Okay, so our next speaker is Kaveh Eftekharinasab, and the title of a talk is Interplay of Global Implicit Functions and Critical Point Theory in Infinite Dimensional Spaces. And yeah, we are glad to have you. You can start now, or you can wait 2 more minutes.
Well, I want to start now. Thank you very much for your introduction. Well, the talk is about the intersection of global implicit functions and critical points theory in infinite dimensional fresh spaces. Well, it is divided into 2 parts. We will consider arbitrary fresh spaces and a class of mapping known as a Kähler C sub S mapping that will serve as our setting in the entire talk. Well, shortly I will explain definitions and motivations behind these considerations. Well, in the first part, we will prove 2 versions of global implicit functions theorem by using the methods of critical point theory. And in the second part, we will apply the theorem being proven to solve 2 problems. First, we will consider initial value problems with a parameter, depending on the parameter. And we will find sufficient conditions that guarantee the existence and uniqueness of solutions over the entire time interval. And we will prove also that the solution map depends smoothly on both the initial value and the parameter. And also, we will generalize to our context the methods of Lagrange multiplier and Nehari methods, which are tools for solving optimization problems with constraint, with the use of the global implicit functions theorem. So first we apply critical points theorem to prove global implicit function, and then we will use these theorems to further develop critical points. That's why it's called the intersection of global implicit functions theorem and critical point theory. This is based on my recent paper, which is available on arXiv. So consider a nonlinear equation. Here, E and G and 0 are the elements of arbitrary fresh spaces, and phi is a continuously differentiable mapping in a sense that I will explain. And I particularly emphasize on arbitrariness and just continuously differentiable of mapping because we aim to obtain the most general result as possible. So first, we are looking for conditions that, sufficient conditions that guarantee that there exists a unique and global solution map, K, such that it does not lose the derivative. Well, that's the terminology of Moser. It means that K maintains the same level of differentiability as the original function phi. So it ensures that these 2 elements, E and G, their relationship is just as smooth as the original function phi. And it is very significant in applications. It facilitates us further analysis without intercounting singularities. That's very important point for us, that our function, our solution map has the same degree of differentiality as phi. So there are 2 possible approaches to tackle such problems. Well, at least to my knowledge. First is to, the most straightforward is first solve it locally and then use to extend the solution to global one by using the classical homotopy theory. It has a rich history that I will not consider today here. And the other method, which is indirect and may seem less trivial, is using the method of critical point theory. So it was in mid-90s that Cartier, in purely topological space, proved global homomorphism theorem using mounting pass theorem. So in a very elegant way. This paper is very significant. It not just revealed the topological ideas behind the critical points theory, but it links actually implicit function theorems and inverse function theorems to critical point theory. And it is the inspiration of our work. So as we will use critical point theory, our first concern is to choose the right notion of differentiability. Well, there are various notions of differentiability in locally convex spaces. And among them, the right one would be what is known today as a Kähler C sub k differentiability. It is highly developed, and more importantly, it facilitates effectively defined compactness conditions on mappings. So it will be clear shortly after the definition of Kähler differentiability and our compactness why we need to choose this particular notion of differentiability. So now I introduce briefly what is this differentiability. It was defined in mid-70s by Kähler for general locally convex spaces. Here is the simplified version for Fresnel spaces, that we consider the topology of compact convergence between the space of continuous linear mappings. And then mapping is called, Kähler's differentiable of class C sub S1 if the directional derivatives in all direction exist and finite, and then derivative is a function from the domain of the function to the space of all continuous linear mapping. That's significant for us that this function must belong to this space. Not all of the other definition will use this space, but it is important that shortly we will see why. So that's the differentiability that we will use. And also to have a better understanding about working in Fresnel spaces, I should mention some distinct characteristic of this space that influence our work. Well, as Fresnel spaces are complete material local spaces, the topology is defined by a sequence of seminorms. So in contrast to the Banach spaces, where a norm provides a single value gauge to gauge the size of the object. But here, as the topology is defined by sequence seminorms, then the estimate of growth rate of object is quite challenging. And also, as the topology, although the topology can be equivalently defined by metric, but these metrics are not intrinsic, and in particular, they are not length metrics. Well, in most cases, in Banach case, they use this fact that the metric is a length metric. They come from the norm. But these two facts also make big difference between the Fresnel case and the Banach case. So here is the rough idea of our approach. Well, to solve this equation, we will not solve it directly. For a given G, we will introduce a mapping such that the solution that we look for is the critical point of this mapping. So indeed, we are transforming our problem to finding the critical point of well-chosen mappings. And here comes to play these tools from critical points theorem, that minimization theorem and mountain pass theorem, and compactness, well known as the Policy-Smith compactness. Well, in the proof of the theorem, I will show how they are all connected. And regarding the mapping that we introduced, here we don't define it explicitly, but we will define it by needed properties that comply with our ingredient. And also we will consider two classes of differentiability, the Kähler C sub 1, C sub S to 1, and local Lipschitz. So as you can see, the idea of the is really pretty simple, that we transform everything to the critical points, finding a problem of critical points. And so the most challenging part is to define this mapping. That's our challenging part. So in order to have a better understanding, I will explain all these ingredients briefly. Well, the Pallas-Smale condition, it was introduced by Pallas and Smale in mid-60s. Well, when they started to study critical points in infinite-dimensional space. And essentially, it provides certain sequence with a convergent subsequence that approaches to critical point. And the definition of Pallas-Smale also works well in our context. Here is the precise definition, that we say the function, the mapping, satisfies the Pallas-Smale condition if for any sequence such that fxi is bounded and the derivative under this sequence approaches to 0, has a convergent subsequence. So as you can see, why we need that the derivative belongs to the space of continuous linear mapping, and actually it is dual. And well-behaved topology, like a compact convergence topology, is very good to work with that. And also, we can generalize it more than we say that F satisfies Pallas condition at level C if we replace this condition that fxi is bounded by fxi approaches to a constant C. In this case, we say that it satisfies at level C. And about concrete examples of function spaces, well, despite that I have been working for some time, some years on this critical point theory, but well, I have immersed myself much to abstract spaces. For now, I don't have examples of functional spaces that satisfy this condition. However, it could be in Mascalto spaces where the elliptic PDE, the solution of elliptic PDE is a critical point. That's a potential where to look, and hopefully, well, we will tackle that problem. So about the minimization. The minimization, if we have a mapping, well, or maybe functional, it's better to say functional, that which is bounded and it is satisfying the Pallas-Smale condition at the level of the infimum, then there exists convergent minimizing a sequence with convergent subsequence that approaches to the minimum of the functional that actually this function gets minimum at this level C, which is the infimum. And this point will be the minimum point. And well, another ingredient that we need is Montaigne-Plus theorem. So it is important for finding the critical points of unbounded functions. So here is roughly the theorem that, again, if we consider functional that satisfy the Pallas-Smith condition at odd level. Now, imagine 2 points, x sub 0 and x sub 1, that roughly speaking, they are separated by the open neighborhood of x sub 0, and we impose this geometrical condition that the infimum of the functional or the boundary of the open neighborhood is more than both of those two values of the function at these 2 points. So visually, it produces a valley between these 2 points, x sub 0 and x1, and a mountain around the boundary. So that's why it's called the Montaigne-Plus theorem. And then this theorem guaranteed the existence of a critical point C, which is more than both of these 2 values. And this is very significant that we have the strictly, C is strictly more greater than A. That's very significant in our proof. And this critical point is obtained by the minimum maximum process. So here, consider the curve that connect these 2 points. And first, we find the maximum of this curve. And then among all of these maximums, the entire continuous map curves that are connecting these 2 properties, we choose the infimum. And that point is the critical point. So these are the main ingredients that we need. Now the statement of the theorem. So we consider here this mapping from this product assess E and product assess E times E by F to G. And we will introduce these mappings from G to non-negative real numbers. And for now, it is from that class of differentiability. And this mapping, it has 2 properties, that it is 0, and also its derivative is 0 only at the 0 element. Now, for any given f in the space f, we'll associate this function g of f, which is the composition I of I and f. And we suppose that we'll assume that this function satisfies the Pallas-Smith conditions at all levels. And actually, we don't need to satisfy at all levels. We just at 2 points, but clearly we don't know what are that points. So we assume that all points. Another assumption is that the partial derivative in the first variable is bijective. Then we can find a unique mapping over the entire space F to E that solves this. That's the solution map, and it is of course a C sub 1. Okay, now the rough idea how to prove it. So for a given G, we associate this function. It is bounded, and it is bounded below, and it satisfies the Pallas-Smith condition at infimum. So the minimization theorem guarantees the existence of a minimizing sequence with convergent subsequence that approaches to a critical point P. And actually, we can show that the value of the function at point P, evaluated at point ng, is equal to the origin, the zero element. So this P is is a solution that we are looking for. And how to prove this one, that it is equal to the zero element? It is based on the, well, mainly three ingredients here, the chain rule and our assumption that the partial derivative is invertible and the definition of I. As you can see, this, our proof is constructive. So we've found this point, and then the next step is to prove that this point is unique. Here, to prove this point is unique, we will use mounting path theorem. And well, we suppose that we have another point that satisfies this equality point E sub 1. And well, we will try to make an environment to use the mounting path theorem for this function and these 2 points. So we will find an open neighborhood U of this point such that our this interval, our this open neighborhood is more than some positive number. And then we will apply the mounting path theorem to find the sequence that approaches to the sequence En that approaches G under the G mapping G, approaches to critical point C more than N, and we will find a convergent subsequence E sub N with the limit H, and we will prove that f of H and G is not the zero element. Here comes to play that this critical point is strictly more than M. As I mentioned earlier, that's the significant for us. But however, this leads us to this leads to the contradiction, because as before, using the chain rule and the invertibility of the first partial derivative and the properties of I, we can prove that it is equal to 0. The value of f at these 2 points is 0. And to define n, we just assign to any g the p that will just be constructed. Okay, well, now here in this statement of the theorem, we assume that it is a differentiable function, but we can also prove it for locally Lipschitz functions. But and also the assumptions, the proof, the ideas will be the same. Well, not the same. Will be well the same. The idea will be the same, but well, we will be needed to use non-smooth analysis. Here, I will briefly explain the non-smooth analysis here that we used is Clark subdifferential. It was defined, it was introduced by Clark in the Banach case, but it works well also in the Fisher case. Now, well, we consider locally Lipschitz function, and then define the generalized directional derivative by using the limit supremum for nearby points H and a small increment T. And then the Clark subdifferential is a set-valued function from the space F to its dual, which is endowed with Weierstrass topology. It is the set of all linear continuous functional such that their values at all points of y is bounded above by the generalized direction derivative. It ensures that this set is, it reflects the slope of the function in all directions y. Okay, so and the point is the critical point if it is point x is the critical point of the function if the zero element belongs to this set. Well, the only thing that here is different from the smooth case is that to define the compactness condition, we actually need assumption that provide us a convergent subsequence that approaches to a critical point. So to define the compactness condition, we'll use to achieve that goal, we'll use these collections of the auxiliary equation, lambda, f, and b. Here, which is defined on the space F. Here is the definition. To define is we will use this family of seminorms that define the weakest star topology for any finite subset of F. This is a seminorm that defines the weak topology on the dual space. And the function lambda is the minimum of such seminorms over the Clark subdifferential, or this set, which is compact in the weakest star topology. So it is a well-defined function. So here it will help us to define the compactness conditions of Pallas-Smith. It is known after the it is known as a Chang Pallas-Smith condition because after the Chang, who was first considered in the Banach case a non-smooth critical points version of compactness condition. So that was the version 2 our global implicit function theorem. Now, the rest is the application of this theorem. So the first, the prime application consequences is the global inversion function theorem. So here is the statement of the theorem that as before we introduce this mapping from F to R is functional, that it is zero and also its derivative zero only at the zero element. Now, if F is of this cross of differentiability between E and F, we have two conditions that for a fixed any fixed F, the associated functional defined as the I evaluated at F minus the value of functional, the difference between these 2 points, and we assume that it satisfies the Peirce condition at all levels. And also another assumption is that the derivative is bijective for any element of the domain. Then this function is a global diffeomorphism. Well, there are there are various results by myself that, it was some years ago, the same results, but with other conditions. Well, the first one was that used also with the method of critical points theory that we don't consider arbitrary spaces because we apply here Nash the inverse function of Nash and Moser, that it requires the function must be tame and at least of class C2. So we drop these assumptions, but we require that the derivative is invertible everywhere on the domain of the at every element of the domain of the function. And also another result which is used by, well, actually is not, it's used the homotopy theory, and it's completely different nature. But here if we have a local diffeomorphism of class between arbitrary Fourier spaces, and if the inverse of derivative is bounded, then it is a global diffeomorphism. So here we have actually is completely different nature conditions, and it is not very clear to me at all that how they are all connected. Okay, now moving on to the solving initial value problems depending on a parameter. This is one of the challenging problem in global analysis beyond Banach spaces. Well, here is the background about known results that it was well, Papenburg at late 90s. He solved this problem not for arbitrary spaces, but for Fourier spaces that they have these two properties. And also, he assumed that this function, the data function, is twice continuously differentiable. And then, well, recently, inspired by some new developments in the inverse function theorem, was improved the results for border classes of spaces known as standard spaces and functions which are weaker differentiable, but other more differentiable, but here we don't have uniqueness. And to prove uniqueness, we need data function to be continuously differentiable and satisfies specific conditions. And much recently, this result was I don't know if it improved or not, because it is not still complete, because here we dropped the assumption that the functions are not standard arbitrary, and we consider the functions are Gaussian differentiable, which is much weaker. But here we don't have unique solution. So now we are aiming to use to solve this problem by using the theorem. We consider arbitrary Fourier spaces, and phi is the, well, continuously differentiable in the Kähler sets. So here is the statement of the theorem. Well, as before, we introduce this mapping. Here, F and E are the spaces where the initial initial point and parameter belongs. Introduce this mapping that it is zero, its derivative zero only at the zero element. And for any phi belongs to this class of functions, then we associate, well, the function g, which is the function I evaluated at the difference between the derivative of psi prime, and the rescaled data function. And we suppose that it satisfies the Pallas-Mail condition at any level. Then we have a unique solution y, which is twice differentiable, and it is defined over the entire time interval, and it is unique. And also the mapping that gives us the solution, probably for a smaller interval, is of class Kähler's C sub 1 in all of the arguments. So I will briefly, I don't know how much time do I have.
You have 8 more minutes.
8 more minutes. So I will briefly give the idea how to prove it. So actually, the idea proof is one of the application of Fourier spaces. Here we reformulate the problem to the functional equation. So first, we rescale it using the simple substitution, and we reformulate it in the functional equation. That's why we want to apply the implicit function theorem. So, and actually, the solution that we are looking for it is the solution of this functional equation. And which is, well, the existence and uniqueness is guaranteed by the global implicit function theorem. And the rest of it is routine. And well, I should move on to the next application. Well, the next application is to generalize the Lagrange multipliers and Harry methods. Well, first, we will introduce a condition for a well-behaved class of mappings. So, if we have well, mappings of this class of differentiability, it is called infinitesimally surjective at the point if the tangent map is surjective. And also we suppose that the kernel of derivative splits the domain. That is, domain is the composition of, well, these two spaces. One is the complement of the kernel of the derivative. Well, such mappings in the Banach case are known as submersions, but submersions in the first cases are much stronger. That's why we don't call them submersions here. Okay, now we will introduce a condition, well, condition S, that for any element of this extended space, well, as before, we associate two functions I and j. I is the function as before, is 0 or derivative as 0 only at the origin. And the function g of v is defined over the space e to well, non-zero reals, which is the I evaluated at difference between this element of the extended space and this order pair. And we assume that it is satisfied the conditions of PS conditions at out level. Well, and here, for such functions that satisfy this condition, we can prove that there exists diffeomorphism from this extended space to E that makes this diagram commutative. So actually, roughly speaking, it says that after the changing of, suitably changing of, well, transforming coordinate system, the function globally behaves like a projection. And it turns out it has a very interesting consequences. That the first one is that if we have a regular value and the pre-image and the function, well, we know that the pre-image is not always in the first case, is not the submanifold. But if it satisfies that condition, as at for some point this condition, at some point of the pre-image, then the pre-image will be the well-behaved submanifold. And even we have more general result that if, which is also is not in general true in the Fresher case, that if we have submanifold in the target space and the pre-image, and if it's transversal to the submanifold in the target space, the pre-image, at some point of pre-image, if that condition is satisfied, then the pre-image is also is the submanifold of this Kähler's well-behaved submanifold. These two results in general are not true for Fresher spaces. And actually, we can use, well, we will use this result to prove the Lagrange multipliers. And the Lagrange multiplier is that we have a functional and we have a submanifold. And we are looking for the critical points of the restriction of F2 submanifold. So the theorem says that if the critical points of field restricted can equivalently be can be described in terms of modified function phi minus mu. Well, here minus, composed by f. Here mu is the element of the double space that effectively accounts the constraint imposed by phi. And if phi is surjective, that mu is unique. So we have a precise and clear description of the critical points of the restriction in the presence of a surjective function. Well, here, these elements of mu element of the double spaces are known as the Lagrange multiplier. Now, well, I will maybe again briefly go to the Neheri method, which we use this theorem to prove the Neheri, well, to generalize the Neheri theorem. The idea is that
I'm sorry to interrupt. You have, formally speaking, 1 more minute, so maybe briefly.
Well, that's the last. I will briefly.
Okay, excellent.
That's sorry. Yeah. Okay. So the idea is that if we have a functional and we have a submanifold, so the question, we are looking for a special submanifold that the functional and the restriction onto the submanifold, they have the same critical points. So such manifolds are known as Neheri manifolds. That is this is the set of all non-zero elements, such that the derivative evaluated at those elements do not vanish. And this set is, although it's called Neheri manifold, is not manifold. We impose 2 conditions on that. The first condition is the existence an open interval of the origin, which has the empty intersection with Neheri manifold to well, avoid singularities, and also the function phi must be of class C sub 2, and the second derivative evaluated at all points must not vanish. And then the final result is that if f is a Kähler C sub S2 mapping, and n is the Neheri manifold that satisfies these 2 conditions, and in F some condition S at some point of this Neheri manifold, then the critical points, they coincide. So that's all. I think I finished right at the time. Thank you.
Thank you very much for interesting talk.